we have a minimum part here, 160 millimeters by 350, and this is inside the flanges. So this is 16 gauge mild steel or 1.5 millimeter, which means that the overalls would be another 3 millimeters on top of these dimensions. I've given it some simple flanges here, 1 inch high. Let's go to Master Bend Cam, and we'll see some of the reasons for this minimum width. If we look at the centering conveyor, we can see that the suction cups, these are the fixed suction cups, these are always down. They're just inside the part. It's possible to make this part without these short flanges here on either side, but it would still be 13.78 wide. This is as close as the centering pins can come. So if we look at the tool centering, we can grab one of these pins and we can see that I can just barely bring it in a little bit more. So we'll bend this part. We'll look at the tool composition. And this is made up of the central wedge, the fixed tools, and the end tools. There's no spacing segments inside when we have this tool setup done. So one short side, 2 short sides. We'll have to do a reposition here. And then we'll come back and do another reposition to get the part out. But that's a minimum part made quite simply, 4 bends. So the next question is, well, how tall a part can we make with these minimum flanges? So here we have an 8-inch tall box with the same inside dimensions, 160 millimeters by 350, 8 inches tall. We'll come to Master Bend Cam. So here we have this minimum base face part with the tallest flanges that we can have. If we look at the centering conveyor, we do have the opportunity to have some suction cups on these flanges, so that's helping us out quite a bit. But still I have the issue with gauging, so it's as close as the gauging can get. We still need to have these minimum number of suction cups on the part. So getting the part into the panel bender is the first issue. But we can make this part with the same process and same repositions as the smaller part. Same tool setup. 8-inch flanges. No repos needed on the short sides. We'll do a repo on the long. So I'll just come back to the standard bend here to show you how close we're getting in on this. So right here, you can see that we're just clearing the rotator. This part was a little wider, I'd have more space. It's just something to consider when we're running maximums with minimums. We're pushing things very close. So can I make a smaller part? Well, we can with the UBC, so let's open up a UBC part. This is a maximum minimum. What we have here is the tallest flange that I can fit inside the UBC clamp. We'll see that in a minute, 80 millimeters. And then I've made a part with the shortest side that I can make, 122 millimeters, but we're going to see that this presents problems. But this is what we call a super tight part. Let's come to Master Bend Cam. So here we are in Master Bend Cam with this UBC part. I have the UBC clamp installed. You can see here that this 80 millimeters is going to be the height of the flange that can fit inside the UBC clamp. Of course, we have to pay attention to if there was return flanges on here. We're going to get to return flanges next. So let's bend this part and we'll see what's going on. Short sides are done as normal, as we saw earlier. And we'll do the flange that I need to step over first. Step over it, get as tight as I can. And now you can see what's happened here. I've had to make a free bend with many moves to try and eke this part out of the, or eke the tooling out of the part. We'll take a look at the side view and we'll go to transparent and run that second to last flange. So here we'll do the step over. And where I'm at, I've stepped over the part. This flange is about as tall as I can make, 80 millimeters. There's a little clearance. And I'm as close to the foot as I can get it. And you can see that the tooling barely fits. And in order to get this part out, the upper tool moves in an arc. So if I grab this upper tool and just drag it and show you what happens, you see that as I bring it up, it's going to collide with the tooling or with the part here. So what we have to do is move it up a little, out a little, up a little, out a little. I'm going to escape out of that. And we're going to run this free bend at a slow speed. And you can see I move up, back, up, and back, and so on until I get clear of the part. Once we're up, we can do a full disengage with the unloading sequence, which clears the part completely. Then we can retract and unload the piece. If we go slightly wider, we don't have to make so many steps to get out. This is 130 millimeters, same part, but just a little bit wider, 130 inside dimension, 5 inches. Come to this part. This part's a little bit wider. Still needed to make a free bend, but it's only done in 2 steps. Let's take a look at this part. Short side, short side, short flange, repo and step over, bend up, 1, 2, and clear. So I had more room to maneuver. If we take a look at this, this bend, just run to the free bend, the bend beforehand. Take a look at the side, and turn transparent on. So now I've got a little bit more room, which means I can take this upper tool up a little further. We can move it. Here's the first step of the free bend, almost to touching. And then we'll have one more manipulator move, pull it back. And then I've got one more move to come clear, and I'm clear. And then the disengage of the unload sequence will get the tool out of the part altogether. We can run unloading, clearing out. The next step is returns. When we have returns on parts, I still need to respect these minimum dimensions, but now inside the tooling. So here I've got a part that's 25 up, 25 in, or about 1 inch by 1 inch returns. And I've maintained the inside dimensions from the inside of the flanges, 350 millimeters, or 13.78, and 160 millimeters, or 6.3 inches. We're going to see this part run. So when we have returns, we have a different dynamic. The tooling must contract to get out of the part, because the part will have been bent over the years. So let's have a look at the part being bent. Part is gauged. Short side is done. Second short side. We'll need to do a small repo here. I've repoed just inside the minimum. This works. And again, just inside the inside of this part. So you can see we're able to contract the part and get it out. Let's run that last bend just in slow speed. You can see here that the part will have to move forward in the disengage. So let's run the disengage. Part moves forward. Tooling contracts, comes up, we can get out. Now, the tooling contracted a small amount, and the manipulator is inside the tools that can do the contracting. So if we watch this again, we'll see that they come up and come in. They've come in a small amount just to clear this return flange. So now the problem will be, if I make these return flanges any deeper, the contraction will be more. And I run the risk of colliding now with the manipulator. So minimums work fine here, provided that the return flanges are a certain dimension or within a range. Let's look at a part that has the same up dimension of 25 millimeters or 1 inch, but I've come in deeper, 35 millimeters. This part looks like this here. Same part, 35 millimeters in, so slightly deeper return flanges, and we're going to see that we get an error. Okay, so we have this part with the deeper returns. Let's run the bender. Speed up. Short sides are fine. Long side. Now, this bend has had a collision between the manipulator and the fixed tools. Let's take a look, and you can see that in order for the tooling to contract to get out of these deeper flanges, it is now collided with the manipulator. So now what was true in a part with 1 inch returns is no longer true. This is 1 3/8 or so. So how do we overcome this? Well, we could put this reposition back a little further, but I'll never get out of it on the second side. So I need to make the part slightly larger in order to get this out with these deeper return flanges. Bender will allow us to make 55 millimeter returns, so 2.17. So that's we're going to come up 2.17 and in 2.17. This still has the same minimums, So now we're going to see an extreme case where I've got the, what are stated as the minimums between the flanges, but I've got the maximum return flanges installed here in this part. Let's take a look at this one. We'll start the simulation. Deep returns, no issue. Now, I repositioned onto the flange face so that I could get a little further in the bend process, but now you can see I really still can't get out of the part. So I'll hit escape. And now the tool compaction has come in almost to the maximum, guaranteed a collision here, no way out of this. So I've got my manipulator in a position where I can get it out when I want to unload the part, but this part is just too short on the short sides to allow me to clear this. We look at the last bend on the third side and see what happens here. This means that this manipulator is back on one of the flanges and this will clear. So I need the part to be at least wider than this with the returns on it. So what does that part look like? This is now the minimums for the inside flanges, so 260 millimeters by 350. I will be able to make this part. So this is the new minimum inside between the bends with maximum return flanges. Let's look at this part. So maximum return flanges with my new minimums, 260 by 350. Alongside, I repo, I'm still inside the face of the part. I can get out. Here I can come back as close as I can. And I can still bend the part and I can still get out. And you can see the amount of contraction that this tool had to have. The manipulator must be back and clear out of the way here. That part works. The next thing we have to consider is with AUT. AUT has two minimums to pay attention to, and it depends on the flange height. So we'll come to our solid model here. If the flanges are 100 millimeters or less, the minimum I can have with AUT is 200 millimeters. And this means that the arc or the travel of the upper tool with the AUT installed has to come up so far, the AUT will still be installed and I can get this part out. So this is as close as I can get. The AUT is still installed. Let's have a look at the part. So I've got my simple part, 200 millimeters inside the flanges, 100 millimeter flanges, 4-inch flanges. And I've got AUT T1 installed on this machine. Here it is up on the AUT bar. So we'll run this part. Then I'll bring in the AUT. And you can see here that I can get the part out. It's under 100 millimeters and the AUT was left installed. Let's look at this from the side. Let's open part. So you can see that the upper tool itself has come up almost as far as it possibly can. With the AUT installed, this means that the tallest part I can just pull out of here needs to be under 100 millimeters. That leaves us clear. If I had a taller part, I would have to take out the AUT tooling. And in order to take out the AUT tooling while the part is still in play, the new minimum has to increase. So when you have a part like this, it comes 400 millimeters between the flanges. If I have an AUT that has, now we're up to 8 inches, let's go maximum. Take a look at this part. Okay, so we'll take a look here and we'll push play. Almost repo, get the AUT in. Now I have to take the AUT out before I can pull the part out. So we'll have a look at this bend from the side. AUT goes in, I bend it. I need room. This will happen in the AUT disinsertion here on the unloading side. So now I need room or space here to extract the AUT tool in order to pull out. The upper tool is up as far as it'll go. This tool must be removed. And so in the AUT disinsertion, now you can see that I've had space to get it out, and now we can retract the part. So The point of the video is to show that, yes, we have minimums, but combinations of these minimums have impacts depending on if there are return flanges, depth of the return flanges, and in the case of AUT, the height of the flanges.